Hello. Continuing on our discussion of topics 3.4 and 3.5, looking at carrying capacity, population growth, and resource availability, kind of like all mishmashed together. So looking at this graph here, again, always look at your axes of the graph to get an idea of what it's showing. X-axis is looking at time frame, y-axis is the size of the population. This is the most realistic type of graph that you would see for like a real population. Population begins with some exponential growth when there's plenty of resources available. Populations can exceed carrying capacity, as you can see here. When a population exceeds carrying capacity, that is called overshoot, a term you need to know. A population cannot overshoot or exceed carrying capacity forever, because eventually the lack of resources is going to catch up with them. And then once that lack of resources catches up with the population will begin to rapidly die off, and that is called dieback or die off or population crash. Boom and bust. And so then what you see over here on the right part of the graph is a lot of fluctuation or oscillation. The population doesn't like perfectly level out or plateau. You do get a little bit of fluctuation above carrying capacity and then below, and then above and then below. It's all based on resource availability. And this is more, again, like a realistic scenario for organisms on the planet that are going to utilize resources and increase their population slightly past carrying capacity, and then eventually they will crash. And that's what you're seeing here. Trying to move myself here. Other things that affect population growth, you've got density dependent factors and density independent factors. Density dependent factors, like it says here, are going to be felt more when the population is larger. Or like I have in the PowerPoint, their intensity will vary based on the density of the population. The bigger the population, the bigger the impact. So some examples of density dependent factors: competition for resources, predation, that's what you're seeing in this graph here, looking at hare versus lynx population. Lynx are predators of hares, and so as the hare population increases, soon thereafter, the population of its predators, the lynx, will increase. Diseases, parasitism, all examples of all examples of density dependent factors. Notice what these density dependent factors have in common. They all tend to be biotic things, living things that are affecting populations. It's kind of the opposite of density independent factors. Speaking of density independent factors, these are things that are going to have the same impact on a population, whether there's 10 individuals or 10,000 individuals. So density independent factors tend to be abiotic things like natural disasters, habitat destruction, and so on and so on. So speaking of populations that are fluctuating, you should be familiar with 4 basic types of patterns here. The first one is stability, or a stable population. I know looking at the graph, you see some overshoot and some die-off, but it is relatively stable. If you were to draw like a best fit trend line in there, it's relatively a stable population. So things like plants in a rainforest, for example, tend to remain fairly stable. And the reason why plant populations in a rainforest tend to remain fairly stable because you've got, constant rainfall, constant sunlight, relatively constant temperatures. A second type of population fluctuation is called eruptive, or erupt, not erupt like a volcano. But eruptive is pretty much where you've got like a huge population boom at one point in time. Looking at the graph here, you can see there was a few of them back in the 1800s. Can you think of an organism that exhibits eruptive patterns? You know, something like insects. Sometimes you get huge, insect booms of population. Algae blooms can be eruptive as well. So that's an eruptive cycle or an eruptive pattern. A third one is cyclic, predictable, kind of like predators and prey, the lynx and the hare that I had mentioned on a prior graph. And then lastly, number 4, basically, no rhyme or reason, irregular. We saw at one point in time there was a huge fluctuation of birds called dunlins. Nobody's entirely 100% sure what causes it. We know there's a lot of interacting factors that cause their fluctuation, and we haven't been able to tease out those different interacting factors yet. So those are your 4 population patterns. There we go. So some more calculations. We've got only like 2 more slides, but it's all math based. So some more math that you need to know. In addition to the math we did on the prior video, looking at exponential growth calculations. This one, as we're looking at population change, or change in population size. So at the top of the screen here, you can see you do need to know 2 things that will increase population size. That's going to be immigration into a population, and obviously births. Those 2 things will increase population size. And then emigration, exiting a population, will decrease the population size, as will deaths. So knowing these 4 things, we can calculate a change in population size with another formula that you will need to memorize. And that formula is this: births plus immigration minus deaths plus emigration. And that's going to tell you what the population size is. B plus I minus D plus E. So right now, get a piece of paper, try it yourself. Let's say we have a population of 52 reindeer. We've got 19 births and 6 deaths, and then 5 reindeer immigrated into the herd and no emigration. Calculate the population size. Press pause while you calculate the population size using the formula on the screen. Once you've calculated the formula, or calculated the population size, here is your answer. B plus I minus D plus E, so 19 births plus 5 immigrants, minus 6 deaths and no emigrants. Excuse me. So do that math. We had 18 additional reindeer, but that's not the population size, because remember, we started with 52 plus the 18 that came from our births and our deaths and our immigrants. So 52 plus 18, your final answer should have been 70 reindeer. Notice I have units involved. My units are whatever organism we're talking about. So again, we use the formula and then add whatever our number is to our original population. So that's another formula that you will need to know. And then my last calculation for now is going to be using that same formula as well as the formula for percent change, which you definitely, again, need to know the formula for calculating percent change. And you probably learned that formula in a variety of other classes. So calculate the percent change in a population of wolves that starts with 14 total wolves. And then in our scenario, we've got 5 deaths, 3 births, and 4 immigrating wolves being added to the pack from a nearby wildlife sanctuary. No emigration, no wolves are leaving the pack, because that doesn't really happen. So think for a second what you would need to do to calculate percent change in the population. The first thing you're going to need to do is actually use the formula that was on the previous slide. But that's not the formula for percent change, but we need to use this formula first to see what our current population in the wolf pack is. So first, like it says, use the formula to determine the change in the size of the wolf pack. So we got to know, like, what are we starting with? And then after you use that, then you will use the formula for percent change to calculate how much the wolf pack changed. So press pause and calculate what you need to do, and then you can check yourself on the next slide after you press play again. So assuming you press pause and now you're checking yourself. So at the top here, we started with 14 wolves, 5 died, 3 were birthed, 4 immigrants, 0 emigrants. So first you need to use this formula, B plus I minus D plus E. You do the math. Final number was 2, so add 2 to your original population of 14. So 14 and 2 is 16. So now we have to calculate percent change because that's what the prompt wants. Percent change, take whatever your new number is minus your old over old times 100. 16 minus 14 is 2. 2 over 14 times 100. So the wolf pop increased by 14%. If you ever use percent change and you end up with a negative number, that doesn't mean you're wrong. It just means that the population, instead of increasing, the population decreased. So that is it. Woo. So again, math formulas, you do need to know them or plug them into your graphing calculator. And so to just wrap things up here, these are your objectives and essential knowledge from 3.4. So can you describe or define carrying capacity? Do you know what overshoot is? Do you know what the environmental implications of overshoot are? And so on and so on. Checking yourself here. And then your learning objectives and essential knowledge for 3.5. Can you explain how resource availability affects population growth? And then look at those essential knowledge statements. Can you explain them? Do you understand them? So on and so on. And as always, if you have any questions about anything, please ask me. And that's it for the first half of Unit 3. The second half of Unit 3, which is topics 3.6 through 3.9, is all about the human population. And there will be a little bit more math involved, but we'll also be talking about like fertility rates and the demographic transition and population pyramids. So, ta-ta for now.